The most convincing robot dog videos you have seen on YouTube are lying to you. They show smooth, perfect walking in MuJoCo simulations and imply that walking is a solved problem just waiting for better cameras or faster chips. The reality check is that visual smoothness hides the fact that quadruped locomotion remains an unsolved control theory challenge when moved from code to steel. We often mistake simulation fidelity for engineering readiness. When you watch a robot dog trot across virtual grass without slipping, it feels like we have cracked the code on legged mobility. The implication is clear. Better graphics and faster processors are the only barriers left before these machines flood our streets. But this belief ignores a fundamental disconnect between how physics engines model reality and how physical hardware actually behaves under stress. The gap isn't about rendering quality or processing speed. It is a failure of control theory to account for chaotic real-world friction and actuator limits that simulations often smooth over. Recent breakthroughs from 2024 through the upcoming years reveal that standard physics engines like MuJoCo oversimplify these complexities, causing direct transfers of simulated gates to fail catastrophically on actual hardware. Consider the work coming out of UC Berkeley by Radosavovich and Malik. Their research confirms a critical insight. While simulations produce visually smooth locomotion, real-world terrain introduces chaotic friction variations that break standard controllers designed on idealized models. What looks like perfect walking in code often collapses when the robot encounters uneven pavement or slippery grass because the controller was never trained to handle physical chaos. This distinction changes how we must view every demo reel from major robotics labs. If a robot looks perfect in a simulation but stumbles immediately upon touching real ground, it is not because the video was fake. It is because the control theory wasn't robust enough to adapt instantly when friction changed or motors hit their physical limits. The unsolved problem isn't making robots move. It is teaching them to survive unpredictability. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. For years, the industry chased complexity, assuming that more parameters and deeper neural networks would eventually bridge this gap. We believed that if we just fed a robot enough data in simulation, it could learn to walk anywhere. However, studies from DLR and TU Delft challenged this hype around deep reinforcement learning directly. They found that a minimalist open-loop oscillator baseline with only tens of parameters outperformed complex neural networks in noisy environments. This finding is startling for the field. It proves that adding more AI complexity often introduces fragility rather than robustness when facing physical reality. A simple algorithm with fewer tunable variables proved more resilient against sensor noise and failures than deep learning approaches requiring thousands of adjustments. Sometimes, less math yields a sturdier robot because there are fewer ways to break the logic when conditions change unexpectedly. The path forward seems to be shifting away from massive, pre-trained policies toward adaptive control methods that can calculate solutions in real time. Researchers at Carnegie Mellon University and Google DeepMind demonstrated this with a 2025 study involving iterative linear quadratic regulator techniques. They achieved real-time whole-body model predictive control on an actual unit Go1 quadruped without relying on custom solvers or extensive sim-to-real tuning. Their approach handled friction and actuator limits by treating the problem as one of mathematical robustness rather than simulation speed. The result was a system that outperformed complex custom solvers by adapting its movements instantly to physical constraints. This suggests that the bottleneck has never been about how fast we can compute, but whether our control laws are stable enough when the robot's motors saturate or slip. Even more critical is understanding what happens when robots interact with their environment beyond just walking on flat ground. A 2024 study by Zhang et al., known as the MQE research, highlights that basic walking becomes an unsolved problem once other agents or objects enter the picture. Standard algorithms fail under adversarial interactions where physical friction and collision dynamics create chaotic states that simple, smooth gate policies cannot anticipate. This multi-agent complexity turns a solved walking problem into an unpredictable chaos scenario. When two robots walk past each other, or when one pushes against a moving object, the physics become non-linear in ways that standard simulation models struggle to capture accurately. The system must react not just to its own balance, but to the sudden changes imposed by external forces. It cannot fully predict until contact occurs. This brings us back to the core realization. Skills can emerge through sampling-based control without offline training or manual pre-specification of contact behaviors. CMU researchers successfully deployed model predictive path integral control on real hardware, allowing the robot to find stable gates in seconds rather than days of simulation time. This approach removes the need for static gate libraries and instead relies on adaptive algorithms that can mathematically account for physical unpredictability as it happens. The future of robotics is not about better graphics or bigger neural networks alone. It is about control algorithms capable of handling the messy, chaotic reality of friction and limits in real time. We are moving from a phase where we ask if robots can walk to one where we demand they know how to control themselves when the world throws curveballs at them. The engineering reality behind the hype shows that visual success does not equal physical readiness. A smooth video is just a visualization of an idealized model, while true autonomy requires surviving the imperfections of steel and friction. As research continues to refine these adaptive controllers, we will see fewer perfect demos and more capable machines working in imperfect conditions. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.